Great, thank you very much. I will just talk very briefly in a very introductory manner, just to let people know about the type of problems I work on. I'm not going to get into details at all. So I'm at the School of Mathematics and Statistics at the University of Melbourne, and I'm a professor of statistics there. Okay. So I work mainly on three types of problems. One of them, functional data, and I've seen quite a few examples of functional data in talks of other people previously, today or in previous days. So for those who don't know what are functional data, just briefly, they are data which are such that for each individual, you observe an entire function or an entire curve. So normally in statistics, we are interested in variables or vectors, so we observe one or several features like salary, blood pressure, age, etc. for a sample of n individuals. Now, when you talk about functional data, for every individual, you observe an entire curve, an entire function, which I've denoted here by x of t. And t belongs to an interval, so it's really a whole curve, a whole function. And so for each individual, suppose you have n individuals in your study, you observe a function. So you observe x1 to xn, but in this case, each xi denotes a function. So just a few pictures to make sure that you know what I'm talking about. So an example of functional data are growth curves. So if you observe a growth curve for a number of children, such as in this case, well, for each child, you observe a function, a curve. So in this picture, you see 93 curves, and each of the curves is a growth curve of one of 93 children. So that would be an example of functional data. Here is another example of functional data where you have Australian rainfall curves. So these curves that you see there, there's about 190 curves, some to the left and some to the right. Each curve corresponds to one weather station in Australia. And what it shows the evolution of rainfall over a year in Australia, where those numbers, the curves have been obtained by doing an average over the years of rainfall in Australia. Here is another example where you see phoneme curves. So people just pronounce a sound or a phoneme, for example, I as in dark or O as in water. And you can turn the speech of somebody into a curve. So you can turn each sound into a curve. For example, here I show you curves that are called log periodograms. And again, for each person who pronounced the sound, you observe an entire curve, which represents the sound that person has pronounced. So you see, there are many examples. I think that was, my last example. So there are many examples in applications where the data that you observe are not vectors, they're not matrices or what, they are entire curves, entire functions. So of course, then you want to have techniques for doing statistics for analyzing this type of data, which again are called functional data. So because when you have functional data, you want to do the same as usual in statistics. You want to do descriptive statistics. That means you want to compute a notion of mean, a notion of variability. You want to do the same kind of problems that we do with vectors. So you want to do classification, you want to do clustering, and we saw some examples of that in some of the previous talks. You want to do regression, you want to do prediction, you want to do everything that you usually do in statistics, but the only thing is that instead of observing variables or vectors, you have a sample of functions, a sample of curves. So the problems that I've been working on in the functional area, and maybe some of you will find some connection to the application that you're working on. One problem I've been working on is that many statistical techniques are designed for vectors. They are not designed for functions. So how do you apply such techniques when you have functions and not vectors? So typically you cannot apply them directly to functions. You have to turn the functions into vectors. And the question is, how can you reduce function to vectors without losing the relevant information for those particular techniques? And I've been working on that type of stuff. So how to replace functions, how to project functions onto vectors and apply standard statistical techniques while retaining the most relevant information from the functions when you go from functions to vectors. So how to reduce the loss of information. So I've been working on that, dimension reduction, where you project functions onto a vector of dimension 2, 3, or 4. And what you find is often it actually works better. The more you are able to reduce dimension, often the better the methods, because you get rid of irrelevant noise or information that was originally in the function. So not only you can apply standard statistical techniques when you reduce functions to vectors, but in addition, you improve performance compared to using the whole functions, because you get rid of the noise. You get rid of stuff that was not very relevant for your problem. Now, the thing is that often there are techniques that are in use in the functional data literature where people just use standard projections, such as principal component or a vection of principal component that can be applied for functions. But the kind of stuff that I've been working on is to show that the standard projections that people use by default to reduce dimension are not necessarily good for functional data. And sometimes it's better to actually think a little bit about what is it that you're trying to achieve and think whether there is a projection that actually optimizes the information for the problem that you're trying to solve. So I'll give you an example. If you want to do classification, clustering, or regression with functional data, often people first reduce their functions to vectors by using principal component analysis. Well, it turns out that often it's not such a good idea. And you can do much better by using other types of projections, such as partial least squares, for example. So this is the kind of problems that I've been working on. And I saw a few talks previously that work on the same type of thing. And I'd be very keen to learn about problems that other people work on. Another thing that I've been working on is that often functional data are not fully observed, and you can only observe fragments of those functions. And I give you here an example. You have growth curves of children, but because the children are only followed for a period of a few years, you cannot observe their entire growth curve. You can only observe a snapshot of their growth curve, which corresponds to the growth over a period of a few years. So you observe fragments. And what I've been working on is, well, what can you do when you only observe fragments of the curves? Can you still apply the standard techniques? No, you can't, because you have missing data. So what can you do? And I've been working on that kind of problems. I just give you an example. I've been working on trying to reconstruct the missing parts of the functions. So from these partially observed growth curves, we've designed several techniques which are unable to try to reconstruct the unobserved parts of the curve. So on the right, you see the way that we try to reconstruct the entire growth curves by using only these fragments of curves. This is one of the examples of problems I've been working on, but I've been doing other stuff. And just to conclude, I have 2 slides. I don't know, Carrie, if I still have a bit of time, a minute or 2.
Yeah, just 1 minute. Yep.
Okay. I'm also working on measurement errors. I mentioned that because I've seen people here working in nutrition, and that's really my main application area in the work I do with measurement errors. And I'm more and more interested in applications as I get older. So I'm definitely very keen on learning about other people's problems. So what I work on is when you observe data, which are not the ones you're interested in. For example, in nutrition, you are interested in long-term energy intake X, but you can only observe an approximation of that long-term energy intake, which is obtained, for example, by interviewing patients about their energy intake. And I work on designing methods that take this inaccuracy into account. And I also work on analyzing aggregated or summarized data. So instead of observing the data you want, you only observe a summarized form. For example, you could observe the maximum of some data, or you could observe the average of some data. And what I work on is to try to design methods which try to disaggregate the information from those aggregated data. And I think I should stop here. Thank you, Kerry.